Hello and welcome to my talk about the catalyst simulation from nano to micro to macro. My name is Andreas Weber and I am a developer at Math2Market. Yeah, this is our agenda for today's talk. So we give a short introduction to catalysts, why do we want to simulate and what can be simulated, and then I will give some examples for the nanoscale, for the microscale, for the macroscale, and at the end some conclusion of all that. Yeah, modeling exhaust treatment bears many challenges on different scales. So for example, the macroscopic flow through the exhaust pipe and catalyst packing, the flow in the catalyst support channels, flow and diffusion inside walls and washcode layer, and inner grain diffusion to the catalytic reaction sites. So yeah, we have different scales and each of them bears many different challenges, and you can answer many different questions on any of these scales here, and you can simulate on every scale here with GeoDict. Yeah, well, and to show that it's really possible, I have brought some examples with me. I will simulate on every scale, and this is on a hot process and a cold process. So I will show you differences in diffusivity, catalytic conversion, or pressure drop on these different scales on different temperature regions. Yeah, well, and I will start here and show you our whole model, and we will zoom in and stop at the different scales. So yeah, first level in, we zoom on some channels that we want to simulate. Then further down, we have a detailed look on that. And even further down, we will see and have a look on the Washcode layer. Yeah, and what you see here will be our models in the better resolution. So here we have our single channels that we want to simulate the flow in, and if we have a closer look onto cutout, we can now here see the better model. Here you see the washcode on the monolith, and if we zoom in more, and you can see here this is our washcode in detail. So let's start and have a look at the nanoscale at the washcode layer. Here on the right you can see our model of the washcode, and what you see at first is a structure with 50% porosity. The largest pore size is 500 nanometers, so we have a really small pores here. And in red we can see the single dots here, and this is more or less what is described here in the text. Washcode layer contains precious metals which act as the catalytic centers. So yes, noxious gases, carbon monoxide, hydrocarbons, they will all react on these red dots here in the porous washcode. And yeah, bear in mind that in our pore sizes that are so small, we may have Knudsen diffusion regime. That means our molecules will rather hit on the walls here more rather than hitting other molecules in this process. Yeah, and we can simulate all this kind of diffusion in GeoDict, and what we simply do is we take molecules and move them around randomly based on their diffusivity. And after the simulation has finished, we can see how far did our particles travel by the displacement, and this tells us our effective diffusivity of our structure here. Additionally, I added that the molecules can be caught on these reactive centers simply to simulate some kind of first order chemical reactions that you will see later. Yeah, and here you can see how a simulated particle movement will look like. So the random movement of the molecule takes place, and occasionally a molecule will hit this reactive center here and then be caught there, so it does not count as active anymore. And later we can use this value of the active count to get a guess how fast is our reaction, or rather how fast can molecules reach our reactive centers here in our structure. Let's have a look at the results of the nanoscale simulation. So here you see different temperatures and then also different thermal velocity. The thermal velocity is the velocity that the random movement of the molecules has, and for sure if there's a higher temperature then you also have a higher thermal velocity. This can be calculated by literature, and we take this value and plug it into our Knudsen diffusivity and get these values for our structure here. So, and as you can imagine, the cold process has a lower diffusivity than the hot process, simply because molecules will move a little bit faster here. The same is the case for the particle diffusivity, which we have simulated using GeoDict. Here, our particles will also collide with other particles, while in the Knudsen diffusivity, we only have wall contacts. As you can see, the particle and Knudsen diffusivity is rather similar in this structure, and this is the case because we are now near to the Knudsen regime and our Knudsen number is more or less 1. So both values are very similar here. And then also have a look at the active particle graphs. So assuming that our molecules will hit an reaction site here, they will be instantly caught, so they won't be active anymore. And then you can see also here the decrease in active particles is a little bit less strong in the cold process than in the hot process. And as you can imagine, this is also because we have a higher diffusion in the hot process, and then molecules will hit this red reaction centers here more likely. Okay, now we are coming to the microscale. At first, we have a look at our new structure here. We have here a monolith with Washcode in red. So our structure that we have seen in the last slides is now here inside this red material, and we have a totally different scale here. Our channel is 1.2 millimeters channel width and height, and channel length is 3 millimeters. Also, this model is 3 millimeters long. But in reality, we want to simulate 10 centimeters of a simulated channel length, and we do this by using periodic boundary conditions. And what we will simulate here is that molecules will be pushed through the channel by the flow, and eventually they will enter the red Washcode by diffusive movement, and they will undergo the reaction inside this red Washcode. So let's have a look at the simulation. We will simply take our molecules and move them with the flow, and we will move diffusive movement to them. And if the particle reaches the end of our model here, it will be re-added at the front so that it periodically moves through our model here until it reaches the desired travel length of 10 centimeters. So this is the real length that we want to simulate. Our residence times are precisely tracked for each molecule, so we have information how long did each molecule will go through the Washcode layer, for example. So let's have a look at the video. We'll see here now particles will move through the channels several times again and again until they finally reach the end here after 10 centimeters of movement. So here we have our results of the microscale simulation. Again, we have a cold and a hot process here for comparison, and we simply take the diffusivity in the core flow from the literature for these different temperatures, and the diffusivity for the Washcode. This is values that we have got from our nanoscale simulation. So we take all these diffusivity values, plug them into our GeoDict simulation, and then we will get these values here. So on the cold process, we see a mean time in the Washcode is only 0.25 milliseconds, while in the hot process it's much more, it's 0.94 milliseconds. And this is also what we can see in the residence time plots down here. So in our cold process, we have a high peak at the 0 mark for our residence time, which means that we have many particles, many molecules that did not even enter the Washcode at all. So there's no reaction possible for them. While on the hot process, we have much less particles, much less molecules, which have never seen the Washcode. So here our peak is moved more or less to the right of the residence time. So longer residence time means better reaction. Yeah, now we have reached our complicated slides now. I will show you how we describe first order reactions with GeoDict. So we assume a reaction of first order in our catalyst layers, and this is not the case in reality, but we can assume it for our simple reaction here. And what happens is we have species A, which is simply reacting to product B while near to the catalyst. So only reactant A will be reduced, while catalyst will not be consumed. Catalyst will stay the same like before. The change in the amount of A is determined by the rate constant K. This is what we get as an input parameter, and it simply says our change in the amount of A is the same like K times our amount of A. In other words, we can reduce this to an exponential trend and say we take our starting species amount and then we multiply by e to the power minus k times t, and t is the time here, so the time from the residence time from the simulation. We can simply calculate how much of our species is left at the end, and then we can do this for all of our molecules that we have simulated, and then simply get the residuing species at the end of our channel. Okay, and here we see the microscale results. So again, we have a hot and a cold process, and we will now simply assume that our reaction rate is the same for both temperatures. So this would totally not be the case in reality, but since I do not know the real reaction rate that we have, I will simply take the same for both cases, and we see differences even if our reaction rate is the same for both hot and cold process. In the cold process we have a residual species amount of about 40%, while on the hot process we only have 2.1% residual species. That means in the hot process much more of our molecules will react or enter the reaction zone at all. So even if our reaction rate is as fast as in the cold process. And if we take a look at the residual histogram, we can also see this trend. So on the left side, the cold process, we see here's a high peak at the 100% mark of our residuing species. This means we have here some particles that have not reacted at all. So this will be the molecules that moved in the middle of our channel, did not touch or enter the Washcode at all. While on the hot process side, we have only really small amount of molecules that did not enter here inside this red region. So almost all particles, all molecules have entered this red material, have fulfilled their reaction. So our last scale is getting bigger and bigger now, the macro scale. Yeah, here you see the model of our macro scale, and differently than before, we here have the 10 centimeter channel length completely resolved, so no periodic conditions here, and we will simulate the flow going through these channels and have a look at the pressure drop. Yeah, we have much less details on this scale, as you can see. So here our Washcode layer is only 1 voxel in thickness here, a little layer inside our channels. So yeah, much less details, but since we do not want to simulate any detailed diffusive movement anymore, we can use this model here. So let's have a look at our simulation. We have Navier-Stokes flow. We have 5 meters per second mean inlet velocity going through these channels. And we're using the Lear solver because we have a high porosity here. And this is suitable for our Lear solver. Yeah, this is the more easy simulation here as the picture shows. So we simply have flow going through these channels, and yeah, we will see how the results turn out.
The Microscale results are here, and again we did both hot and cold process. Here you see we have the same mean velocity of gas flow going through our structure, but due to temperature differences, our gas viscosity and gas density are for sure different. In the cold process, we have a gas viscosity that is lower than in the hot process, while our gas density is vice versa. So the gas density in the cold process is a little bit higher than in the hot process. If we take a look at our pressure drop, we can see that for the cold process it is about 386 Pascal, and for the hot process it is 518 Pascal. The pressure drop will go up if we have hot gas flow. If you also have a look at the Reynolds number, this also makes a great difference comparing hot and cold process. For the cold process, we have more turbulent flow. Its Reynolds number is 135. In the hot process, we have 57 as Reynolds number. So rather interesting results in this, I would say, simple model here.
So now I'm coming to the conclusion. Simulate on every scale with GeoDict. I hope you enjoyed what you have seen, what you can do on this more or less simple example of only this catalyst in different scales. We have seen a nanoscale structure. We have seen that we can simulate Knudsen diffusion with GeoDict. We have seen molecular diffusion and molecule adsorption with AdiDict. We can take some of these results, get it to the next scale, to the microscale. We have seen that we can there simulate molecule movement, residence time, and even first order reaction with AdiDict. So what is our molecule doing? Where is it going? Does it have any reaction on the way? All this stuff is possible to simulate. We can go even further up, macro scale modeling here, simple channel model of our monolith. We can see the pressure drop if we use FlowDict, or we could also simulate filtration of soot with FilterDict. So yeah, with GeoDict you can simulate on every scale. Thank you for your attention.